All right. So today what we're going to do is our first algebra lesson. So lesson 1, we're going to talk about what are called algebraic expressions. Now, algebraic expressions seems a little complicated when you just see it right off the bat. So we're going to talk about the vocabulary and the ideas behind this so that it's not intimidating, right? Think about it. When you first started learning how to spell, did you start with anti-disestablishmentarianism or cat? Right. So you start small, but then as you learned how to spell things, then you were able to spell words that you'd never spelled before just by hearing them the first time, right? By putting things together. And so that's where I want us to be as you move forward. Because remember, from this point forward in your math career, you're going to be going into more and more complicated math ideas. But I want you to start equating that to things that you're comfortable with, like spelling and those types of things. The ideas are not that complicated as long as you develop the vocabulary and the ideas and a good baseline to begin with. Okay? So we're going to start by looking at some vocabulary and talking a little bit about those. Yes?
So, I don't know, what's that one that looks like that?
The square root symbol. Okay. So, but hold on a minute. We'll talk about some. Let's get these, and then we can talk about some other questions. So, what we've been doing so far is we've been dealing with what's called arithmetic. Now, arithmetic, you're just dealing with numbers and some math symbols, right? Now, there are lots of different math symbols, but for the most part, we're talking about addition, good. Subtraction, multiplication, and division, right?
What is it?
Arithmetic.
Is that an E?
That's an M right there, and that's an E. Arithmetic. All right, I'll get better. All right, so arithmetic. And so you have the numbers, and then you have the symbols, and you're just going to do the math, right? So 1/2 times the base times the height. You knew the numbers, so you just use the numbers to be able to do the math, right? Well, that's all well and good when you know all of the numbers, but you're not always going to know all the numbers that you need to work with. So what happens is, with arithmetic, we move on to what's called algebra. Now, the only difference between algebra and arithmetic is the introduction of those unknown numbers. And because you don't want to write some unknown number every time, right? That's very difficult and it'd make it really ugly. What we do is we use letters to represent those numbers. And so you saw this when we did those geometric formulas, right? What did the B stand for? Base. And then we just looked to see which number we wanted to put in place of that letter, right? So those ideas of using letters shouldn't be that new to you. Okay? So here we go. And those unknown letters have a name. They're called variables. And it's important that you understand the language of algebra so that you'll be able to use it. Because when you're given something in the directions, if you have a word you don't understand, it's very, very difficult to follow the directions, right? So make sure we're using the right terminology, okay? So the letters are called what? Variables. And the reason they're called variables is because their values can vary depending on what the context of the sentence you use them in. And you do that all the time without even thinking about it. Right? If I asked you right now, what time is it? What time is it?
12 o'clock.
12 o'clock, okay? But what if I asked you during 6th period what time it is? Would you say 12 o'clock then? No. Did I change the sentence? Still using the word what to represent my unknown, right? What time? But all it's changed is the context. When I answered the question makes you come back with a different number. So I'm asking you a question in words, you're giving me a numerical answer, aren't you? And that answer can vary depending on the context, or in this case, when. So that's what we're going to do with algebra. We've got some unknown number. Does B always have to stand for base? No. And you're going to see lots of different values. Is B always 2? No. It can vary. It can be anything you want it to be or anything your problem needs it to be. Okay? We typically use, at this stage in algebra, we typically use descriptive letters. So like B and H, space, height. So if I was doing horses, what might I use? H, right? We typically use very descriptive letters. Later, you're going to see as it's more advanced, they stop using descriptive letters, and we typically use the same letter all the time. Anybody remember what that is?
X.
X, exactly. Which leads us to a problem. Because we already use X for something, don't we?
Times.
Exactly. We use that as the symbol for multiplication, for times. So we need to talk about how doing algebra also affects the operations. Okay? All right. So let's look first at the building blocks of algebra. Because in arithmetic, remember, all we had were just numbers and symbols, right? Numbers and symbols, mathematical symbols. But in algebra, we've got more than that. We now have all of the same things plus the variables. Luckily, there is nothing else but add, subtract, multiply, and divide. Can you add, subtract, multiply, and divide?
No.
Then you can do anything in mathematics.
No.
Did you say no? Oh, well, can you use your calculator to do it if you can't? You bet. So, you can do anything in mathematics as long as you can do those 4 operations. Now, that's the good news. The bad news is we can arrange and rearrange those operations into infinite varieties to be able to do some very complex ideas, right? But keep in mind that all you have to do are those 4 basic operations. And I'll show you as we move forward that you're never doing anything but those 4 basic operations. Okay? Now, because we introduced the variables, we've changed the building blocks of our mathematical system. In algebra, right, or in arithmetic, you just had numbers and symbols, but in algebra, you have the numbers, the symbols, and the variables. So we have to think a little bit differently about our building blocks. And the building blocks of algebra are called terms. So we're going to talk about the pieces of a term and what makes up a term so that we can always be able to identify them. And you'll see as you move forward why that's so important. All terms have exactly 4 parts. Whether you see them or not, they're always there. Okay? The first part of every term is its sign. You've heard the phrase negative or positive before, right? Well, we're not going to work too much with signs in this course. That's a little bit further on. But the signs are simply the plus or the minus that are in front of a number. So really, it's still addition and subtraction for us, but there always will be a plus or a minus in front. And so we always know when one term stops and the next one begins if we see a plus or a what?
Minus.
Or a minus. Okay? Good. The second part of every term, and here's a word you might not know, is called the coefficient. The coefficient. Now, it's a big word, big fancy word, but all it means is the number. Okay? So it's the number part of your algebraic term. And every number is a coefficient. Okay? So the coefficient is just simply the number part. And these 2 pieces work together to tell you how many of something you have. Right? But isn't that what numbers do? How many students are there in the class? 12, right? 12 tells you how many students, right? So that's what those 2 things do. The next part is something called the base, and the base simply means the variable, the letter. So it can be A, B, C, X, Y, Z, right? Right now, for us, it can be just any letter, but we like to use descriptive ones, right? So they'll change up quite a lot. Later, when you move into pure algebra classes, then you'll probably just use X's and Y's. Mm-hmm.
Are letters like the less common ones ever used? Like, for example, P? Or...
You bet, and you'll see that today. You can use it anytime. So, for example, if you were measuring potatoes, you might want to use
potatoes.
P. Sorry, I can't. Always got to go back to potatoes, don't we?
Jessica really likes potatoes.
All right, excellent. Potatoes are your friend. And then finally, the last part of every term, whether you see it or not, is an exponent. Now, exponents are in your book called indexes, right? But so like we had the exponent of 2, in other words, a square, that means multiply a number times itself, right? So an exponent or an index. I am perfectly happy calling it an index if you don't like the word exponent, but I really want you to know both terms because they're interchangeable and you'll see them both in books as you go. Now, these two pieces of a term also go together and have a specific job to do. What they do is they name the term. They tell you what kind of term you have. And they're always considered together. So it's not an A if it has a square on it, it's an A squared. It's not an A if it has an A to the third, it's an A to the third. Because if you think about what happens to numbers, if we have 2, 2 is just equal to 2, isn't it? But if I have 2 to the second power, that means 2 times 2, which is equal to what? 4. So if you add an exponent, it changes the value. So an A and an A to the second are not the same thing, are they? Right? So if you change an exponent, it changes the value, so therefore it changes the thing you have. Okay? And so there you go. You have how many and the term. You do this all the time. 4 cars in the parking lot. How many? 4. What are they? Cars. All right? So 4x means how many? 4. What kind of thing? X's. Right? X's in that case, right? So there you go. And so you do this a lot, but instead of writing out all the words, we're just going to use letters to stand for the missing words. Okay? All right. Now, that is a term as well. But this is a term that is not algebraic. If you hear the phrase algebraic, what is it that makes something algebraic? The variable. It has to have a letter in it. So this one is just, what this one is called is simply called a number term. So you will still have just number terms, right? But you will also now have algebraic terms. And the only difference between the two is one has a letter in it and the other doesn't. Okay? All right. So we've talked about how the terms change. Now we don't have just numbers and symbols. We have numbers, symbols, and variables, right? And so when you introduce those different ideas, we also need to see how algebra changes the operations. But it really doesn't change the operations. It simply changes the symbols you use to represent them. Because, for example, if you're writing multiplication, generally, if I wanted to say 4 times A, I would use an X to represent the multiplication, right? Anybody see a problem with that in algebra? Yeah, okay. But why would you need to write it a different way?
Well, X can be used to represent a number, and you don't know if it means 4 times A or 4 times X times A.
Exactly. We don't know that this X means multiply or it means X the unknown. But as you were saying, in the book, many times what they'll do is they'll write it using italics or some symbol or some way to write it, and some that I don't know, like that one. And so they'll write it so that you can differentiate the X that means multiply from the X that means X. Well, I really think that because you know where you're going to be doing algebra from now until you graduate, right? And then on into college, that it would be better to be in the habit of just not using the x for multiplication anymore, because you can use alternatives, right? And one of those alternatives is simply using a dot to represent multiplication. The dot means to multiply. Now, I don't see it often in this book that we're using now, but later you'll start seeing it. And so it can be, you can use the dot to represent multiplication. But if you don't want to use the dot, you don't even have to use any operation symbol. Multiplication is the only operation that requires no symbol at all. So if I have a 4 and an A just stuck together like that, what operation do I assume it to be? Multiplication. That literally means 4 times A. Now, can I do the same thing with subtraction? You've got to have the symbol. Addition? Nope. Division? Nope. All other operations require a symbol. The only one that you can assume it's there is multiplication. There you go. Now, you can also do the same thing if you have 2 letters multiplied together. I need no symbol at all. So what does AB literally stand for? A times B. There you go. All right? So that's the only one that requires no symbol at all. Okay. Now, we also need to agree on some rules for how to write things so that they're in a proper order. So say, for example, I have A times 4 times C. Well, all 3 of those things are going to be multiplied together. So do I even need the multiplication symbols? No. But we don't want to just put them together in the order they are. That still means multiply together. But instead, I want to make it neat and clean and tidy. So the first thing I want to do is any numbers should come where?
First.
Yeah. Any number that you have is going to come first. And then I have 2 letters. How do I know which one of them comes first, do you think? Right. If you think about letters, the way you put letters together is by using the alphabet, right? So any letters that you have, you'll always put in alphabetical order. Okay? So it keeps the term nice and clean, right? So what part always comes first?
Number.
The number. And then if you have more than one letter, those letters need to put in what order? Alphabetical. Now, is the same thing true here? Do I need to worry about the order with these? No, because they're not multiplied, they're added together. So it doesn't apply for other operations. This, again, is only the one operation that really changes with algebra, which is multiplication. Sorry?
And it also would be right.
Right, if you start So we've talked a little bit about the language of algebra, right? Algebraic sentences are made up of terms. What we're going to do is talk about what an algebraic expression is then. We know all the building blocks, so now we can discuss what an algebraic expression is. Okay? An algebraic expression is simply a collection or sentence of terms and symbols. By symbols, I mean add, subtract, multiply, and divide, right? Now, what you cannot have is there will never be an equal symbol.
Why?
Because if you have an equal symbol, then you no longer have an expression. You have a different type of problem that's called an equation.
Oh.
Okay? Now, expressions, okay, because they don't have an equal symbol, they can't be solved unless you know every value. In other words, I know that A is 5, so I can do the problem, right? Because I know that I can replace the A with the 5 and do the math, yeah? But if I don't know A is 5, I can't put anything in place of A. I just have to leave it as A. So I can't solve it and get just a numerical answer. And what we're going to do today is we're going to look at how to translate sentences and ideas into algebraic expressions, right? So we're going to look at some sentences, and then we're just going to translate them into algebraic. All right, so this section is called Writing Algebraic Expressions. So again, they're going to go over some of the information that we already talked about. The symbols used when writing algebraic expressions are called variables or unknowns, right? And they stand for some unknown number. For example, suppose there are D dogs in a kennel. The variable D stands for the number of dogs. We don't know what it is, but we know we need a placeholder, so we just use D. So let's look at the first one here, the first example. And then, so if you added 2 more dogs, that means you're increasing it by 2. So you would have D, the number of dogs, plus 2 more dogs, right? So plus 2. We knew how many that were added, but we still didn't know how many we began with. So the one we began with stayed a variable, and then we added 2 to it. So look at example 1. It says, Brent, Scott, and Takesha are sharing a bag of peanuts. Suppose that Brent eats B peanuts. Why do you think they use B for his? What's his name? Yeah. So instead of peanuts, they use B because it's Brent. Yeah. So he ate B peanuts. So Brent ate B peanuts, right? Now, so if he ate B peanuts, it says Scott ate 1 less peanut than Brent. So 1 less, does that mean that he's eaten more or less, or more or fewer?
Fewer.
So fewer, by exactly how many? 1. So Scott then ate the same number of peanuts as Brent, but minus 1. Right? So we still have a B in it. Don't lose your B. It was the same number minus 1. Okay? So now let's do Takesha's. In hers, she ate the same number as Brent, but then she ate more of them. She ate how many more? 3 times as many peanuts as Brent. So, is that going to be adding, subtracting, multiplying, or dividing? Multiplying. And by what number? 3. So 3 times as many. We could write it as 3 times B. Do we need a multiplication symbol there? Nope. So we could just simplify that as plain old what? 3B. All right? So we've translated these into algebraic expressions from a sentence. Okay? All right. And there you see, they didn't translate it. They just went ahead and left it as 3 times B. But a good habit is a good habit, right? Okay. Looking at 7A1, suppose a bus has P passengers. So how many passengers are on the bus? P. I don't know, so we're going to call it P. 7 passengers get off at the next stop. So how many passengers are now on the bus? So if 7 people get off, you are actually subtracting 7. So P minus 7. Can I rewrite that as just 7P? No, because it's subtraction. We have to keep the symbol in. It's not a multiplication problem, right? How easy is that? Okay, let's look at another one. Kurt, Robbie, and Leo play in the same hockey team. Last season, Kurt scored G goals. Robbie scored 3 more than him, and Leo scored twice as many as them. So we have Kurt, Robbie, and Leo, and Kurt scored G goals, right? So Robbie, it says, scored 3 more than that. So what is 3 more than G going to look like?
G plus 3.
G plus 3. We're going to have more of them, right? By 3. So G plus 3. But if you look at Leo's, it doesn't give us a number, but it gives us the expression twice. Twice always has exactly the same meaning. What does it mean to have twice? Do you remember? Multiply by what number?
2.
2, exactly. Just like multiplying by 1/2 is the same as dividing by 2. Twice always means multiply by 2. So how many goals did Kurt have? G. And so 2 times 2 is going to give us what? Oh, be careful. Just, well, no. He just had, it's just 2 times G, which is plain old 2G. Right? Because there wasn't already a number there, right? So twice means twice as many, so 2 times G, which we can then rewrite as 2G. Okay? Excellent. All right. Moving on. Let's look at this one. A man is N years old. How old is he?
No one knows.
Right, we don't know. So we're just going to call it N years. Okay? All right. How old was he 12 years ago? 12 years younger. So he's N years younger. I'm sorry, N years old.
He was debatably not alive.
Minus 12. Hopefully, if he was a man, they wouldn't call a 12-year-old a man or anybody less than that, right? Okay?
I consider myself a man.
A woman. Okay. All right. Moving on. Okay, so the man's wife is 6 years older than he is. Well, again, how old is he? N. And she's 6 years older, so that would be what?
N plus 6.
N plus 6 years. Yeah, N plus 6. Okay, excellent. The man's mother is twice his age. How old is he? N. And twice means multiply by 2. So that's 2 times N. But remember, the number always comes first. So what do we write?
2N.
2N.
Oh,
There you go. All right? So the number always comes first. Okay. So a hotel has X floors with Y apartments on each floor. How many apartments does the hotel have in total? So this time, do they give us any numbers that we know? No.
It's just X, Y.
Right. We have X floors, and each one of them has Y apartments. So that's X times the number of apartments. So X times Y, or just plain old XY. Okay? Could I write it as YX?
Yes.
Technically I could, but what's wrong with it? What should it? Which one of those is the preferred way? Right. Exactly. Alphabetical order. And you're going to see later, especially when we start talking about combining these things, that if they're in alphabetical order, then they look alike. But does an XY and a YX, would you automatically think, oh, those are the same things? No. But if you had an XY and another XY, you could tell a lot easier. So that's one of the reasons we do it as well. Excellent. Okay? All right. So look at this one. My neighbor has X cats. Write an expression for their total number of tails, eyes, and legs. Right? Well, X cats for tails. How many tails does each cat have?
2.
1.
Do you live very close to a nuclear reactor or something? Okay. All right. So 1x, which is just the same thing as saying what? Just x. Think about it. If you have a table, do I say this one table? No, I just say table. So if you only have one of them, you can just use the name of it. Okay? All right, guys, back focus. All right? Eyes. How many? So I need something times x to learn how many eyes. How many eyes does a cat have?
2.
So therefore, the phrase would be what? Come on, guys. The phrase would be what?
2x.
2x. Right? Good. Number of legs.
4.
So how many legs? 4. So 4 times x would simplify to 4x. All right? Couldn't get much easier than this, could it? So here's what I'm going to do, is I'm going to give you some to work on. Okay? Well, we'll do this one because I want you to see the pattern, and this pattern can sometimes be a little different. So in the fridge, there are 2 punnets with strawberries in them, plus 4 strawberries left over, right? So there's 2 punnets plus 4 more left over. Write an expression for the total number of strawberries if 6 have been put into each punnet. How many punnets? 2. How many strawberries did they put in each one in this case? In the first one, it's 6, right? No, they're just giving you they give you a different phrase. So there's 6 in each punnet for the first one, right? Now hold on. All right, now what operation do I need to use if I have 2 of something with the same number in it?
2, then the number.
Okay. Well, 2 what? Stay in focus. It'd be what operation though? So you're multiplying to get more, right? So like the cats. Well, we did the tails, okay? But there were also some strawberries that weren't in a punnet. How many?
4.
So what else do I need up here?
4.
Plus 4, adding 4 more. Now, look at this and can you tell me, is this algebraic?
No.
Why not?
There's no variables.
There are no variables in it. Excellent. Right. So this is not even an algebraic one. So can I then solve this? You bet. Now, they're not going to ask you to, but I could. 2 times 6 is what?
12.
12 plus 4 is?
18.
12 plus 4 is 16, right? Okay. So there are 16 strawberries if that's the case. Okay. Look at C. It says there are S strawberries in each punnet. So S means, do I know how many there are? No. So when I replace it, it's 2 times S plus 4. And I can simplify that. 2 times S is what?
2S.
2S. So 2S plus 4. Yeah. Right? Now, can I go ahead and solve that then, the 2S and 4? Now, I could solve this one because it was not algebraic. Is this one algebraic?
Yeah.
Yes, because it has an unknown in it, right? So can I solve it? No. So all I can do is just put 2S plus 4. Okay? So you see what I'm saying about you can't solve these unless you know every value. So here's where I'm going to give you a chance to do some of your own. So let me just pull this up here so I can get enough. Okay. So we're going to do 6 and 7. We've seen some examples like this, but you're going to work in groups and then you're going to give me the answer. So just going to go around. You 2 guys can work on the first one. So you all do 6A, right? You guys back there, you 3, you're going to do 6B. You 3 do 6C. You guys do 6A. Y'all can do 7A, I'm sorry for you guys. And 7B. And so that leaves y'all with 7C. Okay? Go! You've got 1 minute. One minute. Then we're going to talk now. Present your answer.
So 6 plus 5. With 1 point.
You didn't want to do it like that. Right?
Oh, okay,
Strawberries in there.
wait. My farm is 5 plus 5 is 6. With 1, 2, so 5 plus 5, of course it's 5.
No, we're doing 7.
Yeah, I know. Let's go. Yeah, but
Oh, so that's 4, so that times 2.